The final analog to linear kinematics is angular momentum. And so angular momentum, we use capital L for angular momentum. So momentum in linear motion is P equals mv. Well, m becomes I, v becomes omega. So angular momentum is I omega. And then the torque, just like with momentum, where a change, a net force gave you a delta P over a delta T, a net torque gives you a delta L over a delta T. It changes the angular momentum of the system. You're familiar with some things in angular momentum. And if we were in class face to face, I would demonstrate this using a chair we have where I hold out some weights and I spin around and I bring my arms in and I put them out. You've seen this before. You've done this in an office chair at some point, playing around with a chair that can spin and spin and spin. Okay, so as you bring things closer, you're making I smaller. All right? So momentum, L, is I omega. Momentum is conserved. So as I bring my arms in, that I, your moment of inertia, gets smaller. And since it gets smaller, what has to happen to omega, right? So omega gets larger. So as I bring my arms in, I get smaller, omega has to get larger, so I spin faster. And as I put my arms out, I spin slower. You've seen this before, right? You've seen this before. I've actually used the fact that total energy is linear motion plus rotational motion before to avoid an accident. This was in grad school. I'm moving along on ice. I did not know I was going to be on ice, but I came around a curve, I'm on ice. And so I'm going 1/2 v squared. 1/2 mv squared. All my kinetic energy is in linear motion. I come around a curve, there's ice everywhere, and there's a red light. And I'm on a side road that doesn't get a green light at all until you stop in the intersection, or stop at the intersection, not in the intersection. Bad place to be. So what did I do? All right, I mean, everyone in the car with me was a little freaked out, but I knew how to get the car to really dramatically slow down and come to a stop before we got to the intersection. What did I do? All I did was I drove into the curb and bumped my front right tire, gotta forget which way is right, my front right tire into the curb. And that started the car spinning. So that added another term, 1/2 I omega squared. The total energy was still conserved, so my velocity went down. And as the car is spinning, the tires are spending way more time slowing the car down than if I was skidding in a straight line. And so I've actually used some of these principles. I did some work. I changed my angular momentum. I changed my linear momentum. Energy was still conserved because there wasn't really any non-conservative thing going on other than the little bit of friction with the ice, which eventually brought me to a stop.